Welcome to solution number 10 for ECE 111. This homework set looks at capacitors and RC circuits. Now, we looked at resistors before. Resistors convert current to voltage, and the basic equation for a resistor is V equals IR. Capacitors, on the other hand, store charge. Capacitors are integrators. So if I have a capacitor and there's current going in, the voltage is the integral of the current times 1 over C. So for example, suppose I have a capacitor. Its initial voltage is 2 volts, right here. This is the current going in. What's the voltage versus time? Well, to find that, you integrate, just like we did before. Integral is the area under the curve. So if I start out at 2 volts and I do nothing, I stay at 2 volts. If I then subtract, like right here, the total area is 1/2 base times height minus 3. I'm going to come down 3. 1, 2, 3. Pass through this point. I'll then come down another 3. 1, 2, 3. Come down to here. And then come down about another 1. I'll then go up. So this area is about plus 2. I'll go up 2. Go up plus 4, this area. 1, 2, 3, 4. Go up another 1-ish. Then come down. This area is about minus 2. And then I stay constant. So that's what the voltage is going to look like. It's just like we did before. You just integrate. Add the area under the curve. Problem 2. Suppose I have the following RC circuit. Find the voltage versus time. Now, capacitors are actually integrators. They also satisfy the equation I equals C dV dt. So when I add a capacitor, I've added a first-order differential equation. To figure out what that differential equation is, I figure out what I1 is. I1 is IA plus IB. That's conservation of current. IA is this current. Is V0 minus V1 over 47. IB is this current. 0 minus V1 over 220. That adds together and gives you I1. I1 is C dV dt, and that's C. So here's your differential equation that describes that circuit. Do a little bit of algebra, group the terms together. That's the equation that satisfies it. So if I can solve this differential equation, I can tell you what the voltage is versus time. And that's one of the reasons that you take calculus before you get into electrical engineering. You need to solve differential equations to solve circuits. Anytime you have a capacitor, or next week inductors, in your circuit, it's described by differential equations. Now to solve these, that's something you're going to do in Calc 3, as well as Circuits 1, Circuits 2. In this class, we want to solve using Matlab. So to solve using Matlab, I can use numerical techniques. If I know the voltage V0, V1, I know the derivative. If I know the derivative, I can move forward in time by 10 milliseconds. So from right here, here's t versus voltage. I know the voltage, I know the slope, dV dt. Just move forward in time 10 milliseconds, and that's the voltage change. That's called numerical integration. So that's what I'm doing right here. I'm going to calculate the change in voltage, that's dV1 dt. Move forward in time by 10 milliseconds. This is the new voltage 10 milliseconds later. Or in this case, actually, 2 milliseconds later. Repeat until I get to 2 seconds, and what you get is this. Or in Matlab, I'm going to show what that looks like. Here's my code. I'm going to start out at 0 volts. My initial voltage, or input voltage, is 10. I'm going to step forward in time by 10 milliseconds, my step size. Keep going for 2 seconds. As I run it, here's V0, there's V1. V1 started out at 0, and then it charges up. After 2 seconds, that's the voltage versus time. Now get an equation for that. Stay tuned until you take Circuits 1, Circuits 2. In Matlab, whatever that equation is, that's what it looks like. Another way to solve is using Circuitlab. Build the circuit in Circuitlab, do a transient simulation. So here I'm going to run for 2 seconds. The step size is 1,000 times smaller, 2 milliseconds. Make this a step input, so at t equals 0, this turns on, and the amplitude is 10 volts. Let it run, and here's the output voltage. Same thing we calculated in Matlab. Okay, that's a one-stage RC filter. Now let's look at a 10-stage RC filter. So if I build the circuit with 10 stages, it looks kind of intimidating. This is described by a 10th order differential equation. The equation actually isn't that bad, but look at any given node, like B1. This current I1 is C dV dt. From conservation of current, I1 is IA plus IB plus IC. IA is V0 minus V1 over 47. IB is 0 minus V1 over 850. IC is V2 minus V1 over 47. Doing some algebra, this is the differential equation at node 1. Due to symmetry, it'll be the same at every node 1 through 9. So node 2, just shift the indices, node 3, node 4, and so on. The oddball is node 10, because there is no extra 47 ohm resistor. This guy's not there. Which means that this term won't be there at node 10. Doing those two terms, what you wind up with is node 10, here's the equation, or that's the differential equation at node 10. So the net result is this circuit is described by 10 coupled first-order differential equations. That's also known as the heat equation. The heat equation, our coupled first-order differential equations, is how heat behaves. It's also how first-order, or how RC filters behave. To find the voltage versus time, stay tuned until you take circuits 2. Or in Matlab, I can solve numerically. If I know how the voltage is changing at any given time, I can integrate. So this is set up as a 10 by 1 vector. I can do 10 integrations in one step. Move forward by 10 milliseconds, the step size, repeat for 5 seconds, and here's what that looks like. So if I run this circuit, these numbers come from my calculations. That's the differential equation that describes the circuit. Let it run, and here's what happens. The initial voltage V0 jumps up to 10. That's my forcing function. That charges at V1, that charges at V2, V3, V4, and so on. Then after 5 seconds, I can show you the voltage versus time. Here's V1, V2, V3, V4, and so on. I just solved 10 coupled first-order differential equations, also known as the heat equation. As part of the power of Matlab, if I can write the differential equations, I can solve using Matlab. When you take circuits 2, you'll come up with an equation for the voltages. Whatever that equation is, this is what it looks like. Okay, so that was the first couple of problems. If I check in Circuitlab, rebuild the circuit, do a time simulation, that's what it looks like. Here I only used 4 nodes. If you did 10 nodes, it would be the same. For this homework set, 3 nodes is good enough. Kind of get the idea. The last 2 problems look at eigenvectors and eigenvalues. Now this is kind of confusing. Very few people know what eigenvalues are. Even fewer know what eigenvectors are. This is a topic that you cover in linear algebra, and after you've had linear algebra, most people still don't know what eigenvalues, eigenvectors are. So that's kind of what we're doing here. With the circuit, I can show you what they are. So if I put this in matrix form, here's my differential equations. In matrix form, I can say that the change in voltage is sum matrix times voltage. Here's the matrix. Kind of notice 7 and 7, 6 and 6. These are the diagonal terms. The off-diagonal terms are 21.27. And the oddball is this last one, 22.453. This is your 10 by 10 matrix that describes how the voltages are changing. When you take linear algebra, you'll learn that if I have a square matrix, like a 10 by 10 matrix, I'll have 10 eigenvalues and 10 eigenvectors. Well, in Matlab, I can calculate those. In Matlab, if I input that matrix, so here's one way to input that matrix. It's a sparse matrix. Most of the terms are zeros. The diagonal terms are minus 43.73. The off-diagonal terms are 21.28. Now, Matlab, if I say, what are the eigenvalues, I'll get this. These are the 10 eigenvalues. What those tell you is I have 10 different modes. Some modes decay quickly, some decay slowly, and some are in the middle. If I want to know what decays that way, that's an eigenvector. I've got 10 eigenvalues, I've got 10 eigenvectors. The fast eigenvector decays quickly, the slow eigenvector decays slowly. So if I give it an initial condition that's an eigenvector, the shape will stay the same. That's the eigenvector, that's the mode. The rate at which it decays is the eigenvalues. So for example, let's go to Matlab. So here I input the A matrix, find the eigenvalues, eigenvectors. Suppose I make the initial condition the fast eigenvector. That should decay quickly. If I simulate it, this is running for 0.3 seconds. If you look at that, the shape stays the same. The shape is the eigenvector. Let's run that again. Okay, we go plus minus, plus minus, plus minus, hot, cold, hot, cold, hot, cold. The voltages quickly collapse on each other, or the temperatures quickly equalize. If that's my initial condition, that's an eigenvector. That'll decay very quickly. It decays as e to the minus 84t. Now, suppose I initialize, make the initial condition, the slow eigenvector. This says that'll decay slowly, e to the minus 1.6t. So if I try that, here's the shape, that's the eigenvector. This is decaying slowly. And there's 10 eigenvectors, there's 10 eigenvalues. Pick a different mode, like mode number 9. That will decay as e to the minus 5.38t. So if I run it, notice that the shape stays the same. The shape is the eigenvector. The amplitude is the eigenvalue. This is decaying as e to the minus 5.3t. The next mode decays as e to the minus 12t. So the shape is the eigenvector. The amplitude is the eigenvalue. Okay, last problem. The last problem is what happens if I give it a random initial condition? Well, let's try it. There's my random initial condition. And here's what it looks like after 0.3 seconds. This shape we've seen before. That's the slow eigenvector. Try it again. Get a random initial condition. Then I see the slow eigenvector. What's happening is with a random initial condition, I've excited all 10 eigenvectors. The fast modes decay quickly, leaving the slow mode. That's the slow eigenvector. So that's kind of the nutshell, eigenvalues, eigenvectors. And again, I don't expect this to make complete sense to you. After you've had linear algebra, it still probably won't make sense to you. One of the problems in math is they can't give you examples because it has to apply to mechanical engineers, electrical engineers, civil engineers, business majors, and so on. In this class, we can give you examples. Here's an RC circuit. It has eigenvalues, eigenvectors. And you can see what's happening. The eigenvectors tell you the different modes. The eigenvalues tell you how that mode behaves. If I excite a fast eigenvector, it decays quickly. Excite a slow eigenvector, it decays slowly. In general, I'll excite all the eigenvectors. The fast ones decay quickly, leaving the slow mode. And that is homework set number 10 for ECE 111.